Before milk becomes cheese, before it's filtered, cultured, or cut, it begins a journey where every second, every degree, and every vibration counts. What looks like a quiet flow of liquid is, in truth, a biochemical structure in delicate equilibrium. Inside each drop, microscopic globules of fat float in suspension, held in place by fragile protein assemblies called casein micelles. These structures are not stable by default. They're engineered by nature to last only a short while. The moment milk leaves the udder, its emulsion starts to degrade, unless technology intervenes. And for premium cheese, where the smallest molecular flaw can alter texture or flavor, the margin for error narrows to a fraction of a degree. That's why the logistics of premium milk resemble the precision of a medical operation, more than a simple transport task. Every tanker that rolls down a country road carries not just volume, but integrity, biochemical integrity. The design of these vehicles borrows concepts from naval engineering, particularly from the hydraulic systems used in military vessels. Inside isothermal milk tankers, the flow of liquid is managed much like the controlled movement of fuel in ship pipelines. Turbulence must be suppressed, flow must be laminar, and heat must be evenly distributed. Any unexpected eddy or vibration can disturb the uniformity of the load, triggering microscopic reactions that will only be noticed hours later when the cheese refuses to set. Temperature is another silent saboteur. Milk must remain at exactly 4 degrees Celsius to maintain its microbial balance and enzymatic potential. Even a deviation of 1.2 degrees Celsius can double the speed of bacterial proliferation inside the tank, accelerating protein degradation and compromising the milk's viability for cheesemaking. In practical terms, that means a tanker, arriving just slightly too warm, may carry milk that's chemically unfit for the exacting demands of long-aged cheeses. Time, movement, and the thermodynamics become co-authors in this process. And without precise control, the entire batch can be lost before it even reaches the dairy. To visualize the scale of engineering required, imagine a cryogenic fuel pipeline used on maritime tankers. Thick insulation layers, flow restrictors, and thermal modulation zones maintain exact temperatures across kilometers of pipeline. That same logic now governs milk transport in Europe's premium corridors. Some of the newest milk tankers are, in essence, food-grade cryogenic chambers on wheels, engineered not to cool harder, but to lose less. Their walls are lined with phase-change composites. Their cores are wrapped in smart insulation. The milk inside moves like a slow river, protected from outside weather and internal disruption. At this scale, logistics becomes its own form of silent agriculture. According to data from the Food and Agriculture Organization, the European Union alone moves over 150 million liters of raw milk each week, most of it under strict, near-medical thermal control. These aren't just numbers. They're flows of potential, streams of milk traveling from rural producers to artisan cheese factories, from mechanical pumps on the farm to robotic arms in the processing plant. Each liter a promise, waiting to be cultured, aged, and transformed. And this is only the beginning. Because what happens next, between the road, the tank, and the first microbial fermentation, determines whether that milk will become fine cheese or biochemical waste. Inside a sealed stainless steel tanker, everything appears controlled. The valves are locked. The temperature reads 4 degrees Celsius. The route is timed down to the minute. And yet, fermentation can begin before anyone notices. A thermal drift as small as 2 degrees, barely enough to notice by touch, can start a cascade of changes. The lactose begins to break down prematurely. The acidity creeps upward. And when the milk reaches the cheese factory, its pH no longer supports the intended fermentation. The result? A texture that crumbles, a yield that drops, a flavor profile that fails to develop. The milk looks intact, but chemically, it's no longer what the cheesemaker ordered. This is why thermal control in milk logistics isn't just about temperature, it's about stability. Some tankers now use walls lined with phase change materials, originally designed to protect blood plasma during medical shipments. These materials absorb heat spikes by melting at specific thresholds, creating a thermal buffer between the milk and the unpredictable world outside. When ambient temperatures rise or the tanker stops under direct sun, these inner layers activate silently, absorbing the heat without allowing it to reach the milk. There's no cooling system racing to compensate. There's no alarm, just a passive engineered defense against invisible decay. And sometimes the threat doesn't come from the road, it comes from the schedule. In southeastern Brazil, where milk production is high and distances are short, tankers stop frequently to collect milk from multiple farms. At each stop, doors open, pumps activate, air enters, heat sneaks in. Ironically, these high-density routes, with short distances and constant activity, cause more temperature fluctuations than longer cross-country deliveries. The milk is always moving, always exposed, and every exposure counts. Some cooperatives have begun to change the way they think about last-mile integrity. In northern Italy, a dairy consortium implemented a two-part system: internal thermal inertia, buffers, and external electronic door sensors. The sensors track exactly how long the doors stay open at each stop. If the cumulative exposure time exceeds thresholds, the system flags the batch for secondary testing. Within months of adopting this system, spoilage dropped by 18%. Not because the roads improved, but because the data revealed exactly where the heat was getting in. And this is the lesson hidden inside every sealed tanker. Milk logistics is not a battle of extremes, but of margins. It's not about refrigeration power. It's about foresight, predicting thermal threats before they cascade, designing systems not to fight heat at the last moment, but to deny it entry altogether. In this world, precision is not a luxury. It's the difference between raw material and irreversible loss, between curd and failure, between milk that's alive with potential and milk that's already too late. Milk was never meant to travel. It's a biologically sensitive fluid designed for immediate consumption, not industrial-scale movement. When it's forced onto roads, hour after hour, tank after tank, something begins to change inside. Not visibly, not loudly, but mechanically. Vibrations from uneven pavement, engine oscillations, and minor speed variations all generate subtle turbulence. This movement introduces air, disturbs protein chains, and gradually creates microfoam, tiny bubbles suspended within the liquid. They're silent. They don't rise, but they alter the milk's internal structure in ways cheesemakers cannot undo. In cheesemaking, structure is everything. The proteins must bind in a predictable way. The fat-to-protein ratio must remain exact. And when microfoam spreads, these ratios shift. The milk becomes slightly less dense, slightly more oxidized. It misleads the sensors at the cheese plant. The curd doesn't set with the same elasticity. The flavor develops unevenly. The yield drops by grams per liter, multiplied across thousands of liters. That's an industrial loss with biological origins. To counter this, engineers turn to a seemingly unrelated sector: high-speed egg logistics. Transporting fragile eggs over long distances without cracking them required suspension systems that could adapt to terrain in real time. From this came the idea of gyroscopic dampers, mechanical stabilizers that correct horizontal and vertical movement as the vehicle rolls. Today, these systems are being customized for liquid cargo. Milk tankers equipped with gyroscopic suspension adjust dynamically, absorbing shocks and neutralizing vibrations before they reach the tank's interior shell. The effect is measurable. Studies comparing milk moved in standard passive suspension trucks with that in actively stabilized tankers found a 22% improvement in casein aggregation capacity. In simpler terms, the milk held its protein structure better, leading to more reliable curd formation. The difference between the two wasn't visible to the naked eye, but for the cheese plant, it was the difference between consistency and compromise. In Wisconsin, a cooperative dairy pushed this even further. Their tankers use real-time gyroscopic accelerometers paired with route-responsive driving algorithms. When road conditions trigger excessive oscillation, the system slows the truck automatically. In test phases, they recovered an 11% yield in mozzarella-grade milk just by adjusting vibration exposure. No changes to temperature, no additives, just less movement inside the tank. The strange part is that you can't see the problem. The milk surface appears calm. The tank is sealed. The readings look fine, but inside, millions of microscopic bubbles shift the balance. A biochemical disturbance moving silently toward the factory. Because in dairy logistics, stillness isn't about silence. It's about integrity. And the most dangerous transformations are the ones you never hear. The logistics of milk are no longer a matter of simply keeping it cold. That era of ice, basic insulation, and timed deliveries is ending. What is emerging in its place is a complex interplay of biology, engineering, and data science. Because milk, when destined for premium cheese, is no longer treated as a fluid. It is a biostructural cargo, one with internal architecture, microbial latency, and a volatile chemical profile. Its quality is not just defined by temperature at arrival, but by the journey itself. Its smoothness, its stillness, its stability from molecular shell to final destination. Inside each liter, proteins and fats are suspended in a fragile colloidal network that degrades with time and mechanical stress. This structure determines how enzymes interact during fermentation, how the curd sets, and how flavor evolves in the months that follow. When that structure is disturbed, even subtly, it leaves a signature in the cheese. A slight imbalance in pH, a defect in texture, a delayed ripening curve. These are not problems that can be corrected in the factory. They are inherited errors, legacies of the road. That's why the future of premium milk logistics lies in the transition from reactive cooling to predictive transportation, and it begins by redefining what kind of problem this is. Not a refrigeration challenge, not a mechanical challenge, but a coordination challenge. A question of synchronizing thermal physics, road dynamics, vehicle design, and environmental data in real time. In Norway, where the export of premium salmon depends on minimizing biomechanical trauma during transport, logistics companies have already begun to implement systems that treat fish not as cargo, but as living sensors. Routes are no longer chosen solely for distance. They're chosen for vibration. High-resolution maps are layered with terrain data, road quality indices, traffic behavior, and even solar radiation forecasts. Every variable becomes part of a stress model, predicting not just how fast a vehicle can travel, but how gently it must move. This is the blueprint now being adapted for milk. Inside modern tankers, sensors do more than monitor temperature. They track fluid movement, sloshing patterns, vibration amplitude, and pressure fluctuations. These readings are cross-referenced with topographical data, meteorological input, and even dairy collection schedules to generate a continuously updated risk profile. The goal is not to reach the factory on time, it's to reach the factory with the milk still biochemically intact. Imagine a system where each tanker knows, in advance, when it will face a heat spike from afternoon sun, or where braking patterns on a downhill stretch will agitate the load. Imagine an AI engine that recalculates the route dynamically, bypassing turbulent zones, not for safety, but for protein preservation. Some prototypes already do this. Not only do they adjust speed and suspension in real time, but they also adjust internal flow dynamics by managing baffle behavior and temperature zones inside the tank. It is not just smart refrigeration. It is a thermodynamic choreography. This evolution also redefines the role of the vehicle. No longer a passive carrier, but an active part of the preservation process. The tanker becomes a moving lab, interpreting its own environment and adapting its behavior. The driver becomes a systems operator. The farm, the road, and the factory become nodes in an information network where every liter of milk is tracked, not just by quantity, but by structural health. And yet, the scale is staggering. Over 1 billion liters of raw milk are moved every year for cheese production, across continents, through varying climates, through bottlenecks and border delays. The infrastructure required to support this movement is invisible to most, but it is critical. It is the reason a piece of Parmigiano Reggiano tastes the same after 24 months of aging. It is the reason a log of goat cheese from France reaches Japan without compromising its bloom. This is not convenience. It is strategy. It is engineering on behalf of biology. And the question that hovers over every shipment remains: how many of those billions of liters arrive with their potential intact? Not just cold, not just present, but viable, ready to transform into something precise, structured and enduring. Because in the high-stakes world of premium cheese, the road is not separate from the product. The journey becomes part of the milk's identity, and logistics, once invisible, reveals itself as one of the most advanced forms of agricultural engineering at work today. Did you imagine that moving milk for cheese was such a high-stakes operation?